Hello, this video is going to be, oops, I opened up the wrong section. Oh, yikes. I'm going to change this. Sorry, I just didn't change the title. This will be fixed by the time you look at it. This is section 2.7 on implicit differentiation. Sorry about that. Proofread everything except the title. So we will talk about implicit differentiation in just a moment, but we want to get warmed up with this idea that sometimes we have to apply derivative rules very abstractly. So let's practice this. Suppose that I tell you that f of x is x cubed times g of x. So the idea is, I don't know what g of x is, but whatever it is, I multiply it by x cubed to get f of x. Right, let's rewrite this with the multiplication dot to make it more obvious. Right, so I don't really know what either one of these functions is, but I know how they're related to each other. If I take g of x and I multiply it by x cubed, I get this new function f of x. So let's give an expression for f prime of x. And I'm saying give an expression because we don't really know what the exact formula is. We have to do this somewhat abstractly. But we understand that this is something times something, so we can use product rule. So we're just going to follow the pattern for product rule, and if it feels a little imprecise or abstract, so be it. So I'll just create my scaffolding for product rule, and I'll go one at a time. So by product rule, I start with derivative of the first thing, which would be 3x squared, times the second thing, which is just called g of x, plus the first thing, which is x cubed, times here is where we would put the derivative of the second thing. Well, this is where we just use what we know. If we have a function that is called g of x, then its derivative is called g prime of x. I don't know what that is, but I know that this is following the correct pattern. I have the specific function x cubed times this named function g of x, and I'm not quite sure what it is, but I'm following the pattern. Derivative of the first times the second, plus the first times the derivative of the second. And we could rewrite this if we like, because we notice none of these parentheses are actually required. So that tells us, at least structurally, the pattern for f prime of x. I would need to know exactly what g of x is to fill in the details, but I understand that this is an expression that at least explains something about that derivative. Let's look at another example. Let's suppose h of x is the square root of g of x. And I'm immediately going to rewrite that with a 1/2 power. So here we can take the derivative using the chain rule. My outer function is something to the 1/2. And my inner function is the function that is simply named g of x. So chain rule says it's outer derivative times inner derivative. So my outer function is something to the 1/2 power. My outer derivative is negative 1/2 something, is 1/2 times something to the negative 1/2 power, where that something is g of x. This is my outer derivative. And then my inner function is simply called g of x. So what would be the name for my inner derivative? If my inner function is called g of x, then my inner derivative is called g prime of x. And we could simplify this if we like. I'm just going to leave it that way. It's an expression. We don't know specifically what these functions are, but we're seeing how the derivative of h prime, or the derivative of h, is related to the derivative of g. All right, let's do one more here. K of x is g of x squared over x. So I know this is a quotient. I will need quotient rule as my general pattern. Something times something minus something times something all over something squared. Now, what goes here would be the derivative of the top. I'm going to leave that blank for now because that's the hardest part. And now we'll just fill in the rest. So it's the derivative of the top times the bottom minus the top, which is g of x squared, times the derivative of the bottom, which is 1. So now we just want to focus on what is the derivative of this thing on the top. And we can do that with chain rule. This is something squared. So the outer derivative would be the derivative of something squared, which is 2 times something, and the something is g of x. And my inner derivative is the derivative of g, which is called g prime of x. And I forgot my bottom squared there. So this one is very tough, but we're realizing it is a quotient rule problem with this tricky part where derivative of the top requires chain rule. So just file this away. We're going to need to do this in a little bit. So now we're going to roll out something called implicit differentiation. And I hope that you're already familiar with these words explicit and implicit. These are words that are used in a non-mathematical context, but they mean more or less the same thing in math. Right? So pause a moment and, as best as you can, write down what does explicit mean, what does implicit mean. Right? So explicit basically means something that is fully spelled out, right? Or given directly. Right? I'm telling you exactly what I have. I'm telling you exactly what I'm thinking. I'm telling you exactly what something means. Right? Implicit is related to the word imply. Right? So implicit means maybe we kind of have to read between the lines. Maybe we have to use context. The message is there, but it's not presented directly. So not presented directly. That's good enough. So we're going to realize that sometimes in math we're given information very explicitly. And sometimes in math we're given information implicitly. That the information is there, but it's not handed to us really, really obviously. So let's look at a couple of examples. We know that quite often in math, we're given an equation that has x and y in it, where y is not expressed as a function of x. So for example, if I had the equation x squared y equals 16, I could plug that into Desmos and it looks like so. Right, so every single point on this graph satisfies the equation x squared times y equals 16, but it's not really in the form y equals. But that's okay, right? If I just look at this graph, I can still ask calculus kind of questions. I could notice, for example, there's a point here at negative 2 comma 1. There's presumably a tangent line at that point. Let's see if I can make this a little bit better. Let me just redraw this. There's a tangent line at that point, and a natural calculus question would be, what is the slope of that tangent line? Right? I have a graph, and the graph enough is that graph gives us enough to start wondering about tangent lines and things like that. Right? So the question is, what is the slope of the tangent line at the point? Oh, not negative 2 comma 1. Sorry, negative 2 comma 4. So in this case, what we could do is we could say, all right, I know I have been given this equation. But I also know I can solve for y very easily. I can just divide each side by x squared, which means y is really 16 times x to the negative 2. And slope of the tangent line is given as a derivative. So y prime, also known as dy over dx, I'm going to be using this notation a little more often, would be 16 times negative 2x to the negative 3, which is negative 32 over x to the third. So that's my formula for the derivative, and I specifically want to know what is the derivative at that point. So at x equals negative 2, y prime would be negative 32 over negative 2 cubed, which is negative 32 over negative 8, which is 4, which seems very believable. Right? I could easily believe that this line has a slope of 4. So in this case, even though the equation was given to us with x and y sort of interacting, we could quickly solve it for y and do it like we've done before. Now, let's contrast this with another situation. Suppose I'm giving you this equation, x squared y plus y cubed equals 10. And we just feed it into Desmos or our calculator to get a graph, right? So this is what the graph looks like. And the point 1, 2 is on that graph. I've highlighted it here. And again, I could think about the tangent line, and I want to know what's the steepness. How steep is the graph at that point? Well, we can't do the same thing. In the previous example, y occurred only once, and it was very easy to isolate y. In this example, we're noticing we have y here and y cubed here. And trying to get just one occurrence of y all by itself on one side of the equation, I will tell you it is technically possible if you know some really detailed algebra tricks. But even if you knew those tricks, it would be very, very difficult, right? So this is not literally impossible, but definitely not something we want to do, right? Solving this for y is not desirable. Let's just say that. Maybe it's possible, but it's not something we want to do. So this is where we're going to use a method called implicit differentiation. So I'm going to walk you through the idea and then show you how it works in this example. So sometimes we can't or won't or don't want to, right? Can't/won't solve for y. But we understand that y behaves like a function of x, at least near a certain point. That if I were to zoom in here, right, this certainly looks like we're just looking at some kind of graph, like, oh yeah, right, I have y equals f of x, and that is a graph, right? That looks like the graph of a function. At least around this point, I see no violations of the vertical line test. It looks like the graph of a function. Just the problem is I don't know the formula for that function. So we're thinking of this as what's called an implicitly defined function. We understand that a function relationship is happening. We just don't know its formula. So here's the approach. Usually we're looking to find the slope of the tangent line. And before we do anything, I want to urge you that in cases like this, it's much better to call that slope of the tangent line dy over dx. Even if you're used to the prime notation, don't use it here. It's going to cause confusion. And one reason why, just to give you a heads up, we will be having the derivative and y interacting. And we may have some situation where we're taking y prime times y squared. Now, something that absolutely happens is people see this and they forget the context, and this definitely looks like y to the first times y squared, and they simplify it as y cubed because they didn't notice that this was a prime and not a 1. Right? That's very dangerous. So instead, in contexts like this, we're always going to use that fraction-y Leibniz notation to express the derivative, because when you look at this, it's very obvious this is a derivative and this is not. Right? We're trying to make y and the derivative look very different so we don't accidentally confuse them. So what we're doing here is we're recognizing that we have y as a function of x. Even though we don't have a formula, y behaves like a function of x. So I'm going to rewrite it as y of x to emphasize that. This is not required, but I really recommend you do it. It will help you avoid mistakes. Then we're going to look at this thing and realize that we have a function on each side, and we're going to take its derivative. Maybe we need some fancy rules, so be it. When we take the derivative, we have to remember that the variable is x. We're going to get an equation with some combination of x, y, and dy dx. We probably want to calculate the slope of the tangent at a specific point, so we're going to plug in, and then we'll just solve for dy dx and check if it's plausible. I'm going through this fairly quickly because let's do an example together, then we'll come back and pay attention to what did we actually do here. So I'm just going to make a copy of the problem we were trying to do. So right off the bat, I'm just going to rewrite my equation as x squared times y of x plus y of x cubed equals 10. I really want to understand that even though I haven't solved for it, y is a function of x. So I'm writing it in a way that really looks like function notation so I don't confuse myself. So now what we want to realize is x squared is a function, y is a function, y of x cubed is a function. When I add all these together, this is a very exotic function, but it's a function. And strictly speaking, 10 all by itself is a function. It's a very boring function. So we have a really complicated function on this side and a really dull function on that side, but they're the same. So what I'm going to do is I'm just going to take the derivative of the entire left side, and I'm going to take the derivative of the entire right side. So I'm going to differentiate. And I'm going to remember that x is the variable. Y is a function, x is the variable. So let's do that. The structure of this thing here is product rule. So for my first part, let me just create my product rule scaffolding. I have derivative of the first times the second plus the first times the derivative of the second. Here is y as a function of x. Its derivative would be called dy dx. Again, you can use the primes, but I really recommend against it. People get confused. Now let's take the derivative of this part. And for that part, we need chain rule. This is something to the third power. So by chain rule, it's going to be outer derivative. My outer function here is something to the third power. So its derivative would be 3 times something squared, where that something is just y of x, times the derivative of this inner function. That inner function is the function just called y of x. So its derivative is called dy dx. Right? We're going to be seeing examples where we just have y. Right? And what is the derivative of y? It's simply called dy dx. And now we're not done because we have an equation. All of this is the derivative of the left-hand side. That is equal to the derivative of the right-hand side, and the derivative of 10 is 0. Right? Be very careful about that. There is a tendency, even for me, to somehow recopy this as 10. We're taking the derivative and it's 0. So this is very complicated looking. And now that we're done taking derivatives, if you want, we can write y in a more normal way. We don't have to emphasize that it's a function anymore. We really just needed that for the derivative step because we wanted to truly understand that x is the variable and y is a function. But now I'll go back to writing y just in the normal way, right? It behaves like a function of x, but we don't have to write it that way. So let's remind ourselves, what were we trying to do? We were trying to find the slope of the tangent line at 1, 2. So I've got this equation. It has some x's in it. It has some y's in it. It has some dy dx's in it. I want to know what is the slope of the tangent line, dy over dx, at the point where xy equals 1, 2. So let's plug those in. Everywhere I see x, I'll plug in 1. Everywhere I see y, I'll plug in 2. So I have 2 times 1 times 2 plus 1 squared times dy dx plus 3 times 2 squared dy dx equals 0. Let's simplify those numbers. This is 4. This is just 1 times dy dx. 3 times 2 squared is 12. So So we have 12 dy dx equals 0. I'll group like terms, right? This is just a number. These both have dy dx in it. So I have 1 copy of dy over dx plus 12 copies of it. That makes 13 total. Right, and I can now try to solve for what that derivative is. I can move the 4 to the other side, and I can divide by 13, and I get negative 4 over 13, which is a smallish negative number. Going back to the diagram, that's very believable. We drew that tangent line. The slope is a negative number, right? The number we got is very close to negative 1/3, which seems pretty believable here, right? It's definitely negative, and the height is roughly 1/3 of the width. So now I'll recap what we did again. We recognize that y is a function of x, so I rewrite it, at least temporarily, as y of x. I really want to make sure that at the derivative step, I'm recognizing that it's a function. You can switch it back after you've done that. We have one equation on the left and one equation on the right, right? So one function on the left and one function on the right after we've done that. And we realize I can just take derivatives of everything. Maybe I need to be a little abstract. Here we had to do product rules somewhat abstractly and chain rules somewhat abstractly, but we can apply those rules. So we apply all our derivative rules. We got an equation that had some combination of x and y and dy over dx. But we also knew we were trying to answer a question at a specific point. I'm not going to ask you generally what is the formula for the derivative. There are problems like that in the book. I'm just choosing to skip it. I want to make these a little more concrete. Let's figure out the specific slope at a specific point. So I'm telling you what x and y are, and therefore you can plug them in. And then we just solve for dy over dx. Treat it like a variable you're trying to solve for. Group like terms if you need to, move things to the other side if you need to. Right, this should be pretty easy algebra once you've plugged in the numbers. Okay, let's look at another example. So here I have the curve with the equation xy squared plus y equals 6. And it looks like this. And I want to find the slope of the tangent line at this point where x equals 1 and y equals negative 3. Now this graph is definitely not a function, but the idea is almost all the time, near a certain point, it looks like a function. The graph behaves like a function. And that's enough. Yes, if we zoom out, we see violations of the vertical line test. But if we zoom in, we're noticing nearby, no vertical line crosses the graph more than once. And that's okay, right? So we're not really saying y is always a function of x. We're just saying nearby y behaves like a function of x. So let's try to mimic these steps. Right? So pause, just ask yourself, what should we probably do first? Go back and look at that list. Whenever I give you just bullet points or a list of steps, really honor that. I'm not trying to trick you. I'm telling you, here is a path of steps you can do to get to the answer. So what I've recommended is, let's take each occurrence of y and write it as y of x to emphasize that it's behaving like a function. So I have x times the function y of x squared plus the function y of x equals 6. Now, what do we do next? And if you're not sure, just look at the list. So now we're going to take derivatives. And we need to apply whatever rules we need. So here, I'm going to need the product rule. So by the product rule, it's the derivative of the first times the second plus the first times the derivative of the second. And to take the derivative of this whole thing, I will need chain rule. It is something squared. The derivative of something squared is 2 times that something. Let me make this a little bit cleaner. The derivative of something squared is 2 times that something times the derivative of that something. The derivative of y is just called dy dx. Now we add to that the derivative of y of x, that's just called dy dx, and that's equal to the derivative of 6, which is 0. So this thing looks like a mess, but let's just clean it up. Right, we're done taking derivatives, so we can go back to just calling this thing y. So here I have 1 times y of x squared. That's really just y squared. Here I have x times 2 times y of x times dy dx. I'll move the coefficient to the front. I have an x. Y of x I'll just call y, but I have this derivative dy dx. Here I have dy dx, and that's all equal to 0. Now what should we do? And if you're not sure, check. Don't make it up, just check. So now we'll plug in specifics. I want to know what is the slope of the tangent line at this specific point. Right? We need to take derivatives before we plug in numbers, just like when we're doing it with derivative of an explicitly defined function. But now we can plug in numbers. Everywhere I see y, I'll plug in -3. Everywhere I see x, I'll plug in 1. So this becomes -3 squared plus 2 times 1 times -3 dy dx plus dy dx equals 0. So let's just clean this up and solve. -3 squared is 9. This is -6 dy dx plus dy dx. Be careful here with your like terms. Students have a tendency to see 9 minus 6 and write 3, but those aren't like terms. This is a number. This has dy dx in it. This has dy dx in it. We only want to combine the things that both have dy dx. So I have 9, and then -6 of them plus 1 of them is -5 of them. Still equals 0. I can move the 9 to the other side. I can divide by 5. And I get -9 over -5, which is 9/5, which is roughly 2. Let's look at our graph and see if that's believable. Is it believable that the slope of that tangent line is roughly 2? Sure looks like it to me, right? Just look at this, what I did here. 1 over 2 up, just on the grid marks, right? Definitely looks like it has a slope of 2, or close to 2, right? Not literally 2, but in that ballpark. I'll always give you a picture so you can check. If you're doing homework problems and there isn't picture, feel free to put it into your calculator or Desmos. I want you to notice if it makes sense, and if it doesn't make sense, I want you to realize that maybe you can find your mistake. Okay, so here's another one. Right, this thing, it's this weird shape that's sort of like halfway between a square and a circle. Right, it's more round than a square, but it's more angular than a circle, and it has this equation: x to the 4th plus y to the 4th equals 17. So there's a point here at 2, 1, and I want to know the slope of the tangent line at that point. So I want you to try this one as much as you can. Right? Hit pause as long as you need to. Try to follow the steps as much as you can. Right? If you hit a wall, you can watch the video and maybe hit pause again when you're back up to speed. Okay, so I hope you have tried this. I will write x to the 4th plus the function y of x to the 4th equals 17. Now I will take derivatives of everything. This is 4x to the 3rd. I need chain rule for the second part. Derivative of something to the 4th is 4 times that something to the 3rd. And then the derivative of the inner function would be the derivative of y, which is called dy dx. Derivative of 17 is 0. Let's rewrite y of x just with the name y because that's more familiar. If you feel like you can confidently do all of this without rewriting it as y of x and just remembering it's a function, that is certainly allowed. But I have seen people really mess that up. If you find you have any kind of uncertainty, just write it using function notation temporarily and change it back when you need to. So now let's plug in our specifics. X equals 2, y equals 1. So we have 4 times 2 cubed plus 4 times 1 cubed times dy dx equals 0. 2 cubed is 8, 4 times 8 is 32, plus 4 dy dx equals 0. So 4 dy dx equals negative 32. And so our slope, at least at that point, is negative 32 over 4, which is negative 8. Right? Looking at the graph, that seems very believable to me. Right? It is a very sharp decline, very sharp decrease. So a rather big negative slope makes a lot of sense. Okay, now we're going to see one last example that does not involve graphs, but involves similar thinking. So here we're going to talk about what's called a demand function. So very often in business and economics, people are concerned with how does the quantity of something relate to the price, right? If people know that a lot of items are available for sale, they won't necessarily want to spend a lot of money on it because they know it's not particularly rare. While if something is very rare, if there aren't many of them, they'll want to pay a higher price, right? So, and this is from the point of view of the consumer, right? The consumer is sort of demanding products at different prices. So let's imagine that this business that is selling widgets has done some research and understands that their demand function is given by this equation, where P is measuring the price in dollars. Let's just make that really clear. And X is measuring the quantity of units on the market in thousands. And I'm calling these widgets. I don't know if I've used this example before. Sometimes when people are doing abstract examples, it's just kind of like a fake generic product, right? Rather than pick something in particular and have someone say that that doesn't seem plausible, we'll just call it a widget, right? And in some examples, widgets cost $1. In some example, widgets cost $1,000. And it just changes because we don't really know what it is. But it's nice to have a word to talk about it. Rather than saying we're producing items or producing units, we'll say we're producing widgets. So we just take that this is given, right? This is handed to you in the problem. You don't need to figure out where it comes from. But if we know the number of widgets available out there on the market, this will tell us the market price at which they would all get sold, based upon principles of supply and demand. And I will just tell you that it is equivalent to this formula. So these are two different versions of the same formula. The second one has a less complicated fraction, right? So they both involve fractions, but this one is probably easier to work with. And I will tell you, if we plug in, it's known that if x equals 100, then p equals 1. So what that means is, right, let's just interpret this before we get caught up in the math. This is saying if 100,000 widgets are available, remember we're counting the widgets in thousands, the market price will be $1, right? Namely $1 per widget. Right? The market will sort of assess, is this rare? Is this common? Is this valuable? And it'll even out at basically people will be, at least on average, paying $1 per widget. But the business maybe wants to know how changes in price relate to changes in quantity, right? Maybe we're selling this at a certain price and we're curious, if I sell it at a different price, will I sell more of them? Will I sell fewer of them? How, and by how much? So specifically, they want to figure out this derivative, dx dp, when x equals 100 and p equals 1. And we want to find and interpret this rate. So right off the bat, we need to be really careful. Right? Dx dp is the same as x prime of p. So we're really going to have to change our perspective. In order to do this, our perspective has to be that P, our input here, is the variable. Whatever goes inside here is the name we use for measuring the variable. And X is actually a function of P. Right? That's not what we're used to. We're used to the variable being called X. But here, X measures quantity. Right? I guess in theory we could have called it Q and there's less confusion. But X is pretty common for quantity. So we're trying to find dx dp. P is the variable. So let's look at this equation we have. I will notice that here I have something with x in it. Here I have something with p in it. And I want to emphasize that x is a function of p. So I'm going to rewrite this. And just FYI, there are 5 zeros there before the 1. And I'm actually going to emphasize that quantity is a function of price. So it is x of p. And then the next one here, again, I want to emphasize, I don't really need those parentheses. X is a function of price. Plus 1 equals 3 over p, which I'm going to write as 3 times p to the negative 1, because I know I'm going to take derivatives pretty soon. So now let's take derivatives. And for some of these problems, we want to keep reminding ourselves p is the variable. So over here, I have just a numerical coefficient in front. I'm going to leave that there. 1, 2, 3, 4, 5 zeros before the 1. And then to take the derivative of this thing, I need chain rule. It's something cubed. The derivative of something cubed is 3 times that something squared by chain rule times the derivative of the inside, which is called dx dp. Here, again, numerical coefficients just kind of hang out. Derivative of x of p is called dx dp. Derivative of 1 is 0. I'm not even going to write it. And then over here, coefficient is 3. P now is the variable. I don't need any chain rule here. Derivative of p to the negative 1 would be negative 1 times p to the negative 2. So let's rewrite this. Let's just remind ourselves that x of p was usually just called x. And now let's plug in these specifics. So we want to know this rate of change when they're producing 100,000 widgets and selling them for $1 a piece. So we'll plug in their specifics. X is 100 and P is 1. So 0.00001 times 3 times 100 squared times dx dp. Right, the numbers here are kind of messy. Just follow along with me. Don't really panic if you feel like you would make an arithmetic mistake here. Here we have 0.01 dx dp, and here we would have negative 3 times 1 to the negative 2. So I will just tell you this whole thing cleans up to 0.03. This one I'm just going to recopy. And 1 to any power, conveniently enough, is just 1, so we have negative 3 there. These are like terms, so I can combine them. So I have 0.04 dx dp equals negative 3, which means that dx dp is negative 3 over 0.04, which is pretty awkward. I could multiply top and bottom by 100, and this works out to negative 75. So don't really get too overwhelmed by all the calculations. I just want you to realize that even if we're not talking about graphs, maybe this method works. And what have we calculated here, right? This is the rate at which X changes compared to price, right? So really, let's put some units on this. Negative 75 something per something. X is measuring quantity in thousands of widgets. P is measuring price in dollars. So we might rearrange this as negative 75, oops, not negative dollars, just negative 75,000 per dollar. This is the rate at which quantity changes. So I'm going to try to write this as a sentence, just so you have some idea of this. Maybe we'll do more examples like this in class. Don't get overwhelmed if you find this to be much harder than the other because all the business stuff is abstract to you. But here's basically the idea. Try to type. Okay. So when quantity is 100,000 widgets and the market price is $1 per widget, quantity demanded is decreasing at a rate of 75,000 widgets per dollar. You'll notice I use the word decreasing so I don't have to have the negative. So here is a rough interpretation of this. It's not perfect, but the idea is if we're offering them for $1, then 100,000 people want to buy it. Kind of what this is saying is if we change the price, theoretically, if we change it to $2, there is a decrease in 75,000, right? So basically, if we increase the price by $1, 75,000 fewer people will want to buy it. So it would actually go down, right? We would subtract 75,000 and we would get 25,000, right? And this is a little artificial because it's not instantaneous. What might actually be more plausible, right? Because doubling the price would be very rare. What might be more plausible is if we change the price from $1 to $1.10. At this price, 100,000 people want to buy it. It's going down at a rate of 75,000 per dollar. So if we only change it by 10 cents, it would go down by 7,500. So maybe what it actually means is if they were to change the price from $1 to $1.10, then now the number of people who want to buy it is not 100,000, it's 92,500. And so the business would need to figure out, is it worth it, right? Do we want to sell more of them at a low price or fewer of them at a high price? And depending upon other considerations, maybe one of those is preferable to the other. Here we're just paying attention to the rate of change. We're not making a decision. You need more information to actually make that decision. So again, I realize this example is very abstract. If you're comfortable with the graphs, that's fine for now. Maybe we'll do a little more with this. Okay, this has already been a very long video, and I will stop.